Strange laws of the universe. Look up on a clear night, far from any city, and the sky looks calm, fixed, almost polite. It isn't. Underneath that stillness is a universe that bends time, hides most of its own mass from us, lets particles be in two places at once, and is, right now, quietly flying apart faster than it was a moment ago. None of it needs solving tonight. You don't have to hold on to any of it. Just let it drift past the way starlight does, arriving from somewhere far away and far in the past, asking nothing of you at all. Let's start with something small enough to fit in your pocket that quietly proves Einstein was right. The watch on your wrist disagrees with the one in orbit. Every phone with GPS is quietly running a correction for something most people never think about. Time itself moves at a different speed depending on where you are. The satellites that make GPS work sit roughly 12,000 miles up, moving fast and sitting in weaker gravity than we feel on the ground. Both of those things change how quickly time passes for them compared to us. One effect from their speed, slowing their clocks slightly, and a stronger opposite effect from weaker gravity, speeding their clocks up. Add it together, and the clocks on GPS satellites drift ahead of clocks on Earth by about 38 microseconds a day. That sounds too small to matter. It isn't. Left uncorrected, that tiny drift would make GPS positions wander by several miles within a single day. A road turning into a field, a ship drifting into rocks that aren't really there. So every satellite carries a built-in correction, adjusting its own clock to stay in step with ours, compensating for a fact about time that Einstein worked out on paper, decades before anyone had a way to test it. Somewhere above you right now, a small clock is running just slightly differently than the one nearest to you. Time was never quite as fixed as it feels. Time bends close to home. Further out, space itself starts setting harder rules. The speed. Nothing is allowed to beat. Light moves at about 186,000 miles a second, fast enough to circle the Earth 7 times in the space of one heartbeat. But the strange part isn't the speed. It's that nothing, no signal, no object, no information of any kind has ever been observed going faster, no matter how much energy you add. As anything with mass speeds up, it takes more and more energy to push it faster still, the increase growing steeper and steeper, curving toward a wall it can approach but never actually touch. Reaching light speed itself would take an infinite amount of energy, which is really just the universe's quiet way of saying it isn't going to happen. This isn't a limit of engineering, waiting for a cleverer rocket. It seems to be stitched into the basic structure of cause and effect itself, a kind of speed limit that protects the order of events, so that nothing can outrun its own consequences, arriving somewhere before the reason it left. Every star you can see is, in that sense, sending you a message from its own past, traveling as fast as anything is allowed to go, and still taking years, centuries, sometimes millennia, just to reach your eyes tonight. If light has a speed limit, some things in the universe have gone the opposite direction, collapsing rather than racing outward. A teaspoon of this would outweigh a mountain. When a massive star runs out of fuel and collapses in on itself, most of what's left isn't a planet or a smaller star. It's something stranger, a neutron star. These objects are typically only about 12 miles across, roughly the width of a city, and yet they can weigh more than our entire sun. The collapse crushes atoms so completely that electrons and protons are forced together into neutrons, packed edge to edge with almost none of the space that normally makes up an atom. The result is a density that's difficult to even describe honestly. A single teaspoon of neutron star material would weigh somewhere in the range of 1 billion tons here on Earth, roughly the weight of a small mountain compressed into a spoon. Some neutron stars also spin extraordinarily fast, completing hundreds of rotations every second, flinging beams of radiation out like a lighthouse, which is a story for later tonight. For now, just picture it, a mountain's worth of mass, small enough to hold in your hand, if your hand could survive holding it at all. Some strangeness lives in the very large, some lives in the impossibly small, and it may be even harder to accept. Two particles that act like one, no matter the distance. In the world of quantum physics, two particles can become linked in a way that has no equivalent anywhere in ordinary life. When two particles are entangled, measuring a property of one, its spin, for instance, instantly tells you the corresponding property of the other, even if that other particle is on the opposite side of a galaxy. Einstein famously distrusted this, calling it spooky action at a distance, suspecting some hidden, more ordinary explanation had simply not been found yet. For decades, it remained a philosophical argument rather than a settled fact. Then, starting in the 1970s and 80s, physicists began actually testing it, and entanglement kept winning. Experiments have now confirmed the effect across distances of hundreds of miles, including tests bounced off satellites in orbit. Nothing appears to physically travel between the particles. The universe simply seems to allow this correlation as one of its basic rules. Two particles, born together and then separated by an enormous distance, still behave, in some sense, like they never really left each other's side. If particles can stay connected across any distance, some places in the universe make sure nothing can connect back out at all. The edge you can cross but never recross. A black hole isn't really a hole. It's an object, an extraordinarily dense one, with gravity so strong that past a certain boundary, nothing can escape it. Not a spaceship, not a radio signal, not even light itself. That boundary is called the event horizon. It isn't a physical surface you'd feel yourself hit. For a large enough black hole, you might cross it without noticing anything unusual in the moment at all. It's simply the point of no return, the last place where escape is still, technically, possible. Inside that boundary, all known paths, every direction you could try to travel, lead only further inward, toward a central point where our current physics simply stops giving useful answers. In 2019, humanity got its first actual photograph of one of these boundaries, a dark silhouette ringed by glowing, distorted light, bent around the black hole's gravity at the center of a galaxy called M87, some 55 million light years away. Proof in an image of something theorists had only been able to describe in equations for over a century. A place genuinely photographed where the rules of coming back simply don't apply. Nothing truly escapes, but everything eventually leaks. Even though nothing can escape a black hole in the ordinary sense, physicist Stephen Hawking proposed something in 1974 that surprised almost everyone. Black holes aren't perfectly permanent. They very slowly evaporate. Near the event horizon, quantum effects allow pairs of particles to briefly appear out of space, one falling in, one escaping outward, carrying a tiny amount of energy away with it. Over immense stretches of time, this slow leak, now called Hawking radiation, causes the black hole to lose mass. The timescale involved is almost impossible to picture. A black hole the mass of our sun would take far longer than the current age of the universe to evaporate this way. Trillions upon trillions of years, well past the point when stars themselves have stopped forming anywhere. But eventually, in that unimaginably distant future, even black holes fade, ending, according to the theory, not with a dramatic collapse, but in one final, faint burst, and then nothing at all. Even the most inescapable things in the universe, it turns out, are only inescapable for a while. Not every mystery in space takes trillions of years to unfold. Some took only a few decades to notice, and even longer to explain. The spacecraft that was slowing down for no reason. In the early 1970s, NASA launched two spacecraft, Pioneer 10 and Pioneer 11, sending them out past Jupiter and Saturn and onward toward the edge of the solar system and beyond. By the 1980s, engineers tracking their exact positions noticed something odd. Both spacecraft were decelerating very slightly more than expected. A tiny, consistent extra drag, pulling them back toward the sun by an amount too small to explain with any known force acting on them. For over 2 decades, this became known as the Pioneer anomaly, and it genuinely unsettled some physicists. Proposed explanations range from the mundane to the exotic, a subtle flaw in Newtonian gravity itself at extreme distances, dark matter, even entirely new physics. The real answer, confirmed around 2012 after careful reanalysis of decades of telemetry data, turned out to be quieter than any of those theories. Heat. The spacecraft's own radioactive power generators were radiating heat unevenly, and that faint thermal push, radiating more strongly off one side of the craft than the other, was enough to account for the entire anomaly. Not a new law of physics, just warmth leaking slowly off an old machine, gently nudging it off course for 40 years before anyone understood why. Some anomalies get explained. Some questions are so basic, we've had to sit with them for centuries. Why the night sky isn't blindingly bright. Here's a question that sounds almost too simple to be a real mystery. If the universe is vast and filled with countless stars in every direction, why is the night sky dark at all? If the universe were infinite, unchanging, and evenly filled with stars stretching back forever, then every single line of sight, no matter which direction you looked, should eventually end on the surface of some star. The whole sky, by that logic, should glow as brightly as a sun, day and night. This puzzle is called Olbers' paradox, named for the German astronomer who popularized it in the 1800s, though earlier thinkers had noticed the same problem. The resolution came from something those earlier thinkers had no way to know. The universe isn't infinitely old, and it isn't standing still. It had a beginning, roughly 13.8 billion years ago, meaning light from anything farther than that simply hasn't had time to reach us yet, and the universe's ongoing expansion stretches the light that does arrive from very distant, very old sources into wavelengths we can no longer see with our eyes at all. The dark sky above you isn't empty. It's just further away and further back in time than any light has had the chance to cross yet. The dark between the stars turned out to have an explanation. The dark matter within the darkness has been harder to pin down. Most of the universe is made of something we've never seen. When astronomers measure how galaxies rotate, something doesn't add up. Stars near the outer edges of galaxies move far too fast. Fast enough that, based on the visible mass of stars and gas alone, they should simply fly apart, unable to stay gravitationally bound together. They don't fly apart, which means something else, something with real gravitational pull, but that doesn't emit, reflect, or absorb light in any way we can detect, must be holding those galaxies together. We call this missing mass dark matter, and by current estimates, it makes up roughly 27% of the entire universe, compared to only about 5% made of the ordinary atoms that form stars, planets, and everything we can actually touch or see. Decades of experiments, buried deep underground and shielded from ordinary radiation, have searched for direct evidence of dark matter particles interacting with normal matter. So far, none have succeeded. We know dark matter is there almost entirely through its gravity, through the way it shapes galaxies we can see, without ever showing itself directly. Most of everything holding everything else gently in place, and we've still never actually seen it. Dark matter holds galaxies together. Something else, even stranger, is pulling the whole universe apart. The universe is expanding faster than it should be. For most of the 20th century, the open question in cosmology was simple. Is the universe's expansion, first discovered in the 1920s, slowing down over time the way you'd expect gravity to gradually pull everything back together? In 1998, two independent research teams studying the light from distant exploding stars called supernovae found the opposite. The expansion isn't slowing down, it's speeding up. Something is pushing galaxies apart from each other, and that push is winning against gravity more and more as time goes on. We call this mysterious force dark energy, and by current estimates, it makes up roughly 68% of everything in the universe, more than dark matter, more than all ordinary matter combined. And yet, we don't know what it actually is. It might be a property of space itself, a constant energy built into the fabric of the vacuum. It might be something else entirely, still unnamed. The discovery earned its researchers a Nobel Prize in 2011, recognition for finding something real without yet being able to say what it's made of. Every galaxy you'll never visit is drifting a little farther from you tonight than it was yesterday, pushed by a force we can measure perfectly and still can't name. Some mysteries are the size of the whole universe. Some hide inside a single beam of light, aimed at two narrow slits. A single particle that goes through two doors at once. Take a single particle of light, a photon, and fire it, one at a time, toward a barrier with two narrow slits cut into it, with a detector screen behind to catch where each one lands. If light behaved the way a stream of tiny balls would, you'd expect two bands to build up on the screen, one behind each slit. That's not what happens. Instead, over time, an interference pattern emerges, alternating bands of light and dark, the exact pattern you'd get if each particle had somehow passed through both slits at once and interfered with itself. Stranger still, if you set up a detector to actually watch which slit each particle goes through, the interference pattern disappears. The particles start behaving like simple, individual objects again, going through one slit or the other the moment you observe them doing it. This experiment first performed in its modern form in the 20th century, remains one of the most quietly unsettling results in all of physics, because it suggests that at this scale, reality genuinely behaves differently depending on whether it's being watched. Not a trick of measurement, something the universe itself seems to be doing every time quietly, whether or not anyone happens to be looking. If watching changes what a particle does, there are also things about a particle you simply can't watch clearly at all, no matter how hard you try. You can never know both, no matter how good your tools. In 1927, physicist Werner Heisenberg proposed something that isn't a limitation of technology, but a limitation built into nature itself. You cannot simultaneously know both the exact position and the exact momentum of a particle with perfect precision, no matter how good your instruments become. The more precisely you pin down where a particle is, the less precisely you're able to know how fast it's moving and in which direction, and the relationship works the other way too. This isn't because our measuring tools disturb the particle, though at this scale they often do that as well. It's a genuine mathematical limit, present even in a perfect imaginary experiment with flawless instruments. This uncertainty isn't a small side detail of quantum physics. It's part of the foundation. It's part of why electrons don't spiral into an atom's nucleus and collapse it, and why space itself is never quite perfectly empty. A fact we'll come back to a little later tonight. Heisenberg worked this out largely through pure mathematics and thought experiments, not new equipment. Sometimes the strangest limits on what we can know are found on paper before anyone builds a single new machine to confirm them. Somewhere in every atom around you, right now, a small, permanent blur, nature simply declining to hold perfectly still. If particles resist being pinned down, some resist being fenced in as well, passing through walls that should be able to stop them completely. Walking through a wall that should be solid. In ordinary experience, if you don't have enough energy to get over a wall, you don't get over it. In quantum physics, that rule has a strange exception. A particle approaching an energy barrier, a kind of wall it shouldn't have enough energy to cross, has a real, calculable chance of simply appearing on the other side anyway, without ever having enough energy to go over the top. This is called quantum tunneling, and it isn't a rare theoretical curiosity. It happens constantly all around you. It's part of how the sun produces energy at all. Tunneling allows hydrogen nuclei in the sun's core to fuse at temperatures that, by classical physics alone, would actually be too low for fusion to occur. Without this quiet rule bending, stars might burn far more slowly or not ignite in a usable way at all. It's also the working principle behind certain modern electronics, including some of the memory chips inside phones and computers, where electrons tunnel through barriers deliberately built to be just thin enough to allow it. A wall that should stop everything, quietly letting some things through anyway. One of the reasons the sun above you, right now, somewhere on the other side of the earth, is burning at all. Some rules bend to let things through. One rule, very quietly, only ever moves in a single direction. Why you can't unstir a cup of coffee. Almost every basic law of physics works the same whether you run it forward or backwards in time. Drop 2 billiard balls into a collision, and the equations don't particularly care which direction you call forward. And yet, in ordinary life, time clearly only goes one way. A cup of coffee, once stirred, never unstirs itself. A cracked glass never spontaneously reassembles. Physicists explain this using a concept called entropy, a measure of disorder, or more precisely, of how many different ways a system's parts could be arranged and still look basically the same. There are vastly more disordered arrangements available to a system than perfectly ordered ones. So as time passes, things drift, overwhelmingly, from order toward disorder, not because any law forbids the reverse, but because it's so statistically unlikely as to be, in any practical sense, impossible. Some physicists believe this slow drift toward disorder is the actual reason time seems to move forward at all. That what we experience as the passage of time may simply be entropy quietly increasing everywhere, all the time, in one direction only. Somewhere behind every quiet, ordinary moment tonight, this one included, the universe is very slowly, patiently coming a little more undone. Entropy pulls everything toward disorder. Something else, far larger, is pulling entire galaxies toward a single point. Thousands of galaxies are falling toward something we can't see. In the 1970s and 80s, astronomers mapping the motion of nearby galaxies noticed something odd. Our own Milky Way, along with thousands of other galaxies, across an enormous region of space, all seemed to be drifting in the same general direction, pulled by something with immense gravitational pull. They named it, simply and honestly, the Great Attractor, because for years nobody could say precisely what it was. The region lies partly hidden behind our own galaxy's crowded disk, an area astronomers call the zone of avoidance, where dust and stars block a clear view of whatever lies beyond. Later observations using X-ray and infrared telescopes capable of seeing through some of that obscuring dust suggested the Great Attractor is likely the gravitational effect of a massive concentration of galaxy clusters, an especially dense region of ordinary matter and dark matter, rather than one single exotic object. Even so, our galaxy, along with our entire local group of galaxies, continues drifting toward it at hundreds of miles per second. A slow, silent migration across 150 million light years toward something we're still only partly able to see clearly. You're not standing still tonight. You never really are. Even the ground beneath the earth beneath you is quietly falling toward something enormous, far away in the dark. If the present is still drifting toward something unseen, the past has left something behind that we can still, quite literally, hear the echo of. The leftover glow from the universe's first light. For its first few 100,000 years, the universe was too hot and dense for light to travel freely. Every photon was immediately absorbed and re-emitted by the dense soup of particles surrounding it, like trying to see through thick fog. Then, roughly 380,000 years after the beginning, the universe had cooled and expanded enough for atoms to form properly for the first time, and that fog finally cleared. Light was, for the first time, free to travel in a straight line. That very first light is still out there, still traveling, stretched by billions of years of cosmic expansion into faint microwave radiation, arriving from every single direction in the sky, equally all the time. We call it the cosmic microwave background, and it was first detected, almost by accident, in 1965 by two engineers who initially thought the strange, persistent hiss in their radio antenna was caused by pigeon droppings. It wasn't pigeons. It was the oldest light in the universe, arriving after a journey of over 13 billion years. Small temperature variations within it still mapping out the very seeds that would eventually eventually grow into every galaxy, star, and planet that followed. A faint static, always playing everywhere, quietly containing the very first moment light was ever allowed to travel freely at all. We're a little past the middle of tonight's stories now. If you're still with me, that's all right. Let your breathing settle and let's keep drifting. The fraction of a second, when space grew faster than light. Right after the very beginning, in a fraction of a second so short, it's difficult to even write out meaningfully, around 1/10 trillionth of a trillionth of a trillionth of a second. Many cosmologists believe the universe underwent an almost unimaginable burst of expansion called inflation. During this period, space itself is thought to have expanded by a factor of at least 10, followed by 26 zeros, in less time than it takes light to cross a single atom. This doesn't violate the speed of light limit we talked about earlier, strangely enough, because that limit applies to objects and information moving through space, not to the expansion of space itself. Inflation was proposed in the early 1980s to explain several puzzling features of the universe. Why it looks so uniformly smooth in every direction, and why space, on the largest scales we can measure, appears to be geometrically flat rather than curved. It remains one of the leading explanations, supported by patterns found in that same cosmic microwave background light, though the exact mechanism that triggered and ended inflation is still an active, open question in physics today. In less time than it takes to blink, or even to begin to blink, the universe may have gone from smaller than an atom to larger than a grapefruit, the fastest anything has ever happened, right at the very start of everything. Space itself once stretched faster than light. A century later, we finally learned how to feel that same fabric ripple. We finally heard two black holes collide. In 1916, Einstein's equations predicted something that even he doubted could ever actually be detected: gravitational waves, ripples in the fabric of space-time itself, created whenever massive objects accelerate, especially in violent events like collisions. The trouble was scale. By the time a gravitational wave from a distant collision reaches Earth, it stretches and squeezes space by an almost impossibly tiny amount, far smaller than the width of a single proton, across a detector stretching miles. On September 14th, 2015, an instrument called LIGO, using laser beams, bounced down two perpendicular 4-kilometer tunnels to detect exactly this kind of infinitesimal stretch, finally succeeded. It detected the unmistakable signature of two black holes, each around 30 times the mass of our Sun, spiraling into each other and merging over 1 billion years ago in a collision so violent it briefly outshone every star in the observable universe, entirely in gravitational waves rather than light. The discovery, confirmed and announced in 2016, earned its lead researchers a Nobel Prize the following year, proof a full century after Einstein first wrote the prediction down that space really does ripple. A collision older than our solar system, finally arriving as the faintest possible tremor, felt for the first time on a quiet September morning. If space itself can ripple, some physicists wonder whether our entire universe might be only one ripple among countless others. Ours may not be the only universe. Some versions of inflation theory, the same rapid expansion idea from a few chapters ago, lead to an unusual further possibility that inflation, once it starts, might not stop everywhere at once. In this idea, called eternal inflation, our own universe might be just one region where inflation ended, forming a stable, structured universe like our own, while inflation continues elsewhere, endlessly spawning other separate regions, each potentially becoming its own universe with its own laws. This is genuinely speculative territory. Unlike the earlier topics tonight, the multiverse hypothesis isn't something we've directly observed or measured. It's a mathematical consequence that falls out of certain versions of inflation theory, taken to their logical conclusion. Serious physicists disagree about how seriously to take it, partly because it's difficult to imagine how we could ever test it directly, since by definition, other universes would be forever outside our own observable reach. Still, it remains one of the more quietly fascinating ideas at the edge of cosmology, not a proven fact, but a genuine possibility that respected physicists continue to explore and argue over. Somewhere beyond everything we'll ever be able to see, there may be other skies entirely, with other rules, or there may simply be nothing at all. We may never get to know which. Whether or not other universes exist, ours has a strange enough secret hiding in what looks, at first, like nothing at all. Empty space isn't actually empty. Take a box, remove all the air, all the light, all the matter. A perfect vacuum. By most everyday definitions, that box now contains nothing. Quantum physics disagrees. Even a perfect vacuum still contains what's called zero-point energy, a small, irreducible amount of energy that can never fully be removed, tied to the same uncertainty principle we talked about earlier tonight, because a particle's position and momentum can never both be perfectly fixed. Space can never settle into a state of absolutely zero energy either. One consequence of this shows up in something called the Casimir effect, first predicted in 1948 and later confirmed experimentally. Place two uncharged metal plates extremely close together in a vacuum, and a very slight force will push them together, caused by a difference in the quantum fluctuations of space on the inside versus the outside of the gap. Some physicists suspect this same background energy of space might even be connected to dark energy, the mysterious force accelerating the universe's expansion, though the numbers, when calculated directly, don't yet match up cleanly, leaving it as one of the more stubborn unsolved puzzles connecting the very small to the very large. Even the emptiest space you could ever build is quietly never quite empty at all. Some strangeness hides in space, invisible by nature. Some strangeness hides in plain sight, in the light of a single star, and no one can fully explain it either. The star that dims in ways nobody can fully explain. In 2015, citizen scientists helping sift through data from NASA's Kepler Space Telescope flagged something odd about a star cataloged as KIC 8462852, now better known as Tabby's star, named after astronomer Tabitha Boyajian, who led the study of it. Most stars dim very slightly and predictably when a planet passes in front of them. Tabby's star did something stranger. Its light dipped by unusually large and irregular amounts, at one point dropping by over 20%, far more than any planet could plausibly cause, with no clear repeating pattern. The irregularity briefly made headlines with a genuinely dramatic hypothesis that the dimming might be caused by a vast megastructure built by an advanced civilization, partially enclosing the star to capture its energy. It was a serious enough possibility astronomers pointed radio telescopes at the star, listening for any artificial signal. None was found. Further study, published over the following years, instead pointed toward an uneven cloud of orbiting dust, possibly from a shattered comet or a disintegrating small planet as the more likely, if less dramatic, explanation. Though even that explanation doesn't account for every detail of the star's behavior perfectly. A single, ordinary-looking star, quietly flickering in a way we still can't fully explain. Not aliens, most likely, but not entirely solved either. Not everything strange in space is a star. Some of it is a planet, with nothing to orbit at all. Planets wandering with no star to call home. Most planets we know of orbit a star, held in place by its gravity, warmed by its light, but not all of them. Rogue planets are worlds that drift through space entirely untethered, either flung out of their original solar system by gravitational interactions with other planets, or in some cases, possibly formed on their own, directly from collapsing clouds of gas and dust, the way small stars do, without ever gathering enough mass to actually ignite. These worlds are extraordinarily hard to find, since they emit no light of their own and reflect none from a nearby star. Astronomers detect them mainly through a technique called gravitational microlensing, watching for the brief, telltale way a rogue planet's gravity bends and magnifies the light of a distant star it happens to pass in front of for the watching astronomer on Earth. Based on the handful detected this way, some estimates suggest there could be billions of these starless worlds drifting through our galaxy alone. Cold, permanently dark, silently crossing distances that would take light itself years to cross, belonging to no solar system at all. Somewhere out there tonight, entire worlds are drifting through absolute darkness, belonging to no sun, following no orbit, going wherever the last gravity that touched them happened to send them. Some collisions fling planets into the dark. Others, far more violent, forge something you might be wearing on your hand. The wedding ring that may have been forged in a cosmic collision. For a long time, astronomers weren't entirely sure where elements heavier than iron, including gold, platinum, and silver, actually come from. Ordinary stars, through nuclear fusion, can build elements up to iron, but building anything heavier requires far more violent conditions. In August 2017, scientists got a rare, direct answer. Both LIGO's gravitational wave detectors and dozens of telescopes around the world simultaneously observed the same event. Two neutron stars, the same impossibly dense objects from earlier tonight, spiraling into each other and colliding about 130 million light years away. The collision, called a kilonova, released a burst of matter and energy so extreme that it forged enormous quantities of heavy elements within moments. One single event estimated to have produced gold and other heavy elements, totaling many times the mass of the Earth. It was the first time astronomers had directly observed both the gravitational waves and the light from the same cosmic event, confirming decades of theoretical work all at once, and offering for the first time real observational evidence for where a meaningful share of the universe's gold actually came from. Any gold you're wearing tonight is, very plausibly, older than the Earth itself, forged in a collision between two collapsed stars, long before our own sun had even begun to form. Not every cosmic mystery has been solved as neatly. Some are still just a signal and a question mark. The 72-second signal nobody has ever explained. On August 15, 1977, an astronomer named Jerry Amon, working on a radio telescope project, scanning the sky for unusual signals, was reviewing a stack of printouts days later when one particular reading caught his attention. The signal was strong, 30 times louder than the normal background noise, and it lasted a full 72 seconds, exactly the length of time a signal from a fixed point in deep space should take to pass through the telescope's field of view as the Earth rotated. Amon circled the reading in red pen and wrote a single word beside it: wow. The signal appeared to come from the direction of the constellation Sagittarius at a very specific radio frequency, one closely associated with neutral hydrogen, often discussed as a plausible frequency for interstellar communication, since hydrogen is the most common element in the universe. Despite extensive searching in the decades since, using far more sensitive instruments, the same signal has never been detected again from that spot or any other. Proposed explanations range from a passing comet's hydrogen cloud to a rare astronomical event to equipment reflection. None has been proven, and none has fully satisfied every researcher who has studied the data. 72 seconds captured once on a single sheet of paper in 1977, still all these decades later unexplained. Some questions have no answer yet. This next one is even more basic. Why anything exists to ask questions at all? Why the universe is made of something instead of nothing? According to our best understanding of physics, the Big Bang should have created matter and antimatter, its mirror image opposite, in exactly equal amounts. That's a problem because matter and antimatter destroy each other completely on contact, converting entirely into energy. If the early universe had truly formed with perfectly equal amounts of both, they should have annihilated each other almost immediately, leaving behind a universe of pure light and energy. No stars, no planets, no galaxies, and no one around to wonder about any of it. Clearly, that isn't what happened. Somehow, for every roughly 1 billion pairs of matter and antimatter particles that annihilated each other in the early universe, one extra particle of ordinary matter was left over, unpaired, surviving the mutual destruction. Everything you can see, touch, or become, every star, every planet, every person who has ever lived, is built entirely from that tiny leftover imbalance. Physicists still don't fully understand what caused matter to be favored over antimatter in the first place, and finding the answer remains one of the most actively pursued open questions in particle physics today. You exist, quite literally, because of a rounding error in the early universe. One extra particle in a billion, left over, with nothing left to cancel it out. That leftover matter built stars, planets, and eventually laboratories, where physicists recently broke a rule that had stood unquestioned since the 1800s. The crystal that moves without ever losing energy. For nearly 2 centuries, one of physics' most basic laws held that any system left alone without energy being added will eventually settle into its lowest energy state and stop changing, a ball rolling to the bottom of a bowl and staying there. In 2012, physicist Frank Wilczek proposed something that seemed to break this rule: a time crystal, a structure that could continue changing in a repeating pattern indefinitely, even in its very lowest energy state, without consuming or losing any energy to do so. Motion, essentially, for free, forever. It sounded, to many physicists, uncomfortably close to a perpetual motion machine. Historically, a strong warning sign of a flawed idea. But time crystals don't actually violate the law of energy conservation. They simply exhibit motion in time, the way an ordinary crystal exhibits repeating structure in space, without that motion ever being harnessed to do external work. In 2017, several research teams succeeded in actually building time crystals in the lab using carefully arranged atoms manipulated with lasers and magnetic fields, turning a theoretical proposal into a real, physical, repeatedly verified object within just 5 years. A structure that moves in a steady, repeating rhythm, forever, without ever running down. Not magic, just a corner of physics we hadn't looked closely enough at before. Time crystals move without losing energy. There's a much older, stranger liquid that moves without losing anything at all. The liquid that climbs out of its own container. Cool, ordinary helium down to within a few degrees of absolute zero. Colder than the space between stars. And it does something no other common substance does. It becomes a superfluid. A superfluid flows with absolutely zero viscosity, meaning zero internal friction of any kind. Poured into a container, superfluid helium doesn't just sit still like an ordinary liquid. It can creep up and over the inside walls of its container entirely on its own, forming an incredibly thin film, and drip back out over the outer edge, seemingly climbing against gravity, driven by nothing but its own complete lack of resistance to itself. If you set superfluid helium spinning in a container, it will continue spinning, apparently forever, with no motor and no outside energy required to keep it going. A direct, visible, real-world demonstration of a quantum effect happening at a scale you could genuinely watch with your own eyes, rather than needing a laboratory instrument to detect it indirectly. This behavior, first observed and properly explained in the late 1930s, was one of the earliest clear signs that quantum mechanics, usually associated with the invisibly small, could, under the right conditions, shape the behavior of a liquid you could actually hold a beaker of. A liquid with no friction at all, quietly escaping its own container, obeying no instruction except its own strange, frictionless nature. Superfluid helium bends the ordinary rules of liquid. There's an equally strange rule about twins, one thankfully that doesn't require going anywhere near absolute zero. the twin who ages slower, simply by traveling. Imagine identical twins. One stays home on Earth, the other boards a spacecraft, travels out at a significant fraction of the speed of light, then turns around and comes home. When the traveling twin returns, they will genuinely be younger than the twin who stayed behind, not through any illusion or trick of perspective, but as a real physical difference in how much time each twin actually experienced, a direct consequence of the same time dilation we talked about at the very start of tonight in a much smaller, gentler form with GPS satellites. For decades, this was purely a thought experiment, occasionally debated for a subtle asymmetry in the reasoning, since, from the traveling twin's point of view, it's technically the earthbound twin who seems to be moving. The resolution lies in the fact that only the traveling twin actually changes velocity, accelerating and decelerating to turn around, breaking the symmetry between the two perspectives in a real, physically measurable way. We don't need to send actual twins into deep space to confirm this anymore. Astronauts who spend extended time aboard the International Space Station TR Aveling roughly 17,500 miles per hour do age very slightly slower than people on the ground. Astronaut Scott Kelly, after nearly a year in orbit, returned measurably, if only by a fraction of a second, younger than his identical twin brother, Mark, who remained on Earth. Real identical twins, one of whom is now, quite literally and quite precisely, a little bit younger than the other, because of where he spent a single year of his life. Space and time bend around speed. They also bend around mass in a way that turns entire galaxies into lenses. Galaxies, so massive they bend light into rings. Einstein's general relativity predicts that massive objects don't just pull on other objects with gravity. They actually bend the space around them, and light, traveling through that bent space, bends along with it. The effect is usually far too subtle to notice around ordinary objects, but around something truly massive, an entire galaxy or cluster of galaxies, the bending can become dramatic enough to visibly distort the light of whatever lies behind it as seen from Earth. This is called gravitational lensing, and in the most extreme, perfectly aligned cases, it produces something astronomers call an Einstein ring, the light of a distant galaxy bent evenly, all the way around the mass in front of it, forming a genuine glowing circle in space, a natural lens millions of light years wide. Astronomers now use this effect deliberately as a tool. Massive galaxy clusters act as natural magnifying glasses, allowing telescopes to see even more distant, faint galaxies behind them that would otherwise be completely invisible, effectively borrowing the gravity of one galaxy to see clearly into the depths behind it. Some of the most distant galaxies we've ever photographed were only visible to us at all because something enormous and much closer happened to bend their light gently into view. Some particles get bent by gravity on their way to us. Others pass straight through everything, including you, without ever noticing it's there. Trillions of ghosts are passing through you. Right now, as you listen to this, roughly 100 trillion neutrinos, tiny, nearly massless particles, mostly produced by nuclear reactions inside the sun, are passing directly through your body every single second. You will never feel a single one. Neutrinos interact so weakly with ordinary matter that the vast majority pass straight through the entire Earth, from one side to the other, as though the planet simply isn't there at all. This makes them extraordinarily difficult to detect. Physicists build neutrino observatories deep underground or deep within Antarctic ice, using enormous tanks of ultra-pure liquid, waiting patiently for the extremely rare moment when a neutrino happens to actually collide with an atom inside the tank, producing a tiny, detectable flash of light. Despite their near total indifference to matter, neutrinos carry real scientific value. They travel in an almost perfectly straight line from wherever they're produced, including the cores of distant supernovae, offering astronomers a rare, direct glimpse into events and processes that light itself cannot escape quickly enough to show us. Trillions of tiny, indifferent travelers passing through you, through this room, through the entire Earth, every second of your life, and never once leaving so much as a trace. Neutrinos pass through everything without touching it. The universe itself, on the largest scales, has a shape we're still only just beginning to trace. Nobody is entirely sure what shape the universe actually is. On the scale of a whole universe, ordinary questions like, what shape is it, become strange. Space itself might curve, the way the surface of a sphere curves, or a saddle curves, or it might be simply perfectly flat, stretching on in every direction like an endless sheet. Measurements of that same cosmic microwave background light from earlier tonight allow physicists to measure this curvature fairly precisely by studying the exact sizes of temperature variations within it. So far, every measurement points toward the universe being remarkably close to flat, geometrically at the largest scales we can observe. Close to flat is doing a lot of quiet work in that sentence, though. Current measurements can't fully rule out a very slight curve, one so gentle it would only become detectable across distances far larger than we're currently able to observe, meaning the universe could still, technically, curve back on itself over some vastly larger scale we simply can't see from here. It's a strange thing to sit with. We can measure the shape of the entire universe more precisely than almost anything else in physics, and the honest answer is still very likely flat, as far as we can tell from the small corner we're able to see. The whole universe, and we still can't say for certain whether it curves back on itself, somewhere far beyond anywhere we'll ever get to look. The universe's overall shape is still uncertain. One small thought experiment, taken seriously, makes even a single closed box uncertain too. A box where nothing is settled until you look inside. In 1935, physicist Erwin Schrödinger proposed a thought experiment, never actually carried out, meant to illustrate just how strange quantum superposition becomes when applied to something larger than a single particle. Picture a sealed box containing a radioactive atom with a 50% chance of decaying within an hour, wired to a mechanism that would release a poison if it does. Until the box is opened and observed, quantum mechanics equations technically describe the entire system, atom, mechanism, and outcome together, as existing in a superposition of both possibilities at once. Schrödinger didn't propose this to suggest that outcome was literally true. He intended it as a pointed criticism, a way of showing how uncomfortable it becomes when you take the strict, literal mathematics of quantum superposition, usually discussed only for single particles, and apply it without adjustment to an everyday-sized object. Physicists still don't fully agree on how exactly a system moves from quantum uncertainty into one single definite outcome upon measurement, a genuine, unresolved question at the philosophical heart of quantum theory, still debated seriously, nearly 90 years after Schrödinger first posed it as a complaint rather than a proposal. Not a real box, and never a real cat. Just a very sharp, very old question about where exactly uncertainty ends and reality begins, still sitting quietly unopened. Some uncertainty lives in a thought experiment. Some spins through the sky in a rhythm so precise it once helped confirm relativity itself. Lighthouses in space, spinning hundreds of times a second. Some neutron stars, the impossibly dense collapsed cores from earlier tonight, are born spinning extremely fast and beam intense radiation out from their magnetic poles as they rotate, sweeping across space the way a lighthouse beam sweeps across the sea. We call these objects pulsars, and if that beam happens to sweep across Earth as it spins, we detect it as an extraordinarily precise, regularly repeating pulse of radio waves. The fastest known pulsars rotate several hundred times every single second, spinning fast enough that a point on their surface would be moving at a meaningful fraction of the speed of light. Pulsars were first discovered in 1967 by astronomer Jocelyn Bell Burnell, who noticed an unusually precise, repeating radio signal in her telescope data, so regular that she and her colleagues briefly, half-jokingly, nicknamed it LGM-1 for Little Green Men, before identifying its true natural source. Because their rotation is so remarkably stable, some pulsars keep time more precisely than almost any clock built on Earth, and have been used by astronomers as natural laboratories to test Einstein's theories of relativity with extraordinary precision out in deep space. Somewhere out there tonight, dozens of collapsed stellar cores are spinning hundreds of times a second, sweeping their light across the galaxy in perfect rhythm, like lighthouses built by no one, for no one, that we simply happened to notice. One last mystery before we let the night close. Not a distant one this time, but one already quietly underway, above us right now. Our galaxy is already falling toward its neighbor. The Andromeda Galaxy, our nearest large galactic neighbor, sits roughly 2.5 million light years away, and it's approaching us right now at around 250,000 miles per hour. In roughly 4 billion years, current measurements suggest Andromeda and the Milky Way will begin to collide and gradually merge into a single, larger galaxy, sometimes informally nicknamed Milkomeda by astronomers in the papers that model it. Despite both galaxies containing hundreds of billions of stars, the collision won't actually involve much star-to-star violence at all. The distances between individual stars, even within a galaxy, are so vast that direct collisions between them will be exceedingly rare. Instead, the two galaxies will slowly pass through and around each other over hundreds of millions of years, their gravity gradually reshaping both into swirling tidal streams before eventually settling into one new, larger galactic shape entirely. No one alive today, and no descendant of ours for well over 100,000 generations, will ever see even the beginning of it. It's simply already happening, quietly, gradually, on a timescale too vast for any single human life or any human civilization to witness even the opening moments of. Somewhere above you tonight, two entire galaxies are already, slowly, patiently falling toward each other. A merger already in motion that won't finish for longer than humanity has existed, multiplied many times over. That's where we'll leave it tonight. A watch that disagrees with the one in orbit. A speed nothing is allowed to beat. A teaspoon heavier than a mountain. Two particles that never really left each other. An edge you can cross but not recross. A slow leak even from the darkest places. A spacecraft slowed by nothing more than its own warmth. A sky that's dark for a reason. Most of the universe still unseen. An expansion that keeps on accelerating. A particle that goes through two doors at once. A blur nature refuses to sharpen. A wall that lets some things through anyway. A cup of coffee that will never unstir itself. A pull toward something enormous, still mostly hidden. The oldest light there is. A fraction of a second when space outran light. A ripple finally heard a century after it was predicted. Other skies maybe that we'll never see. A silence that was never really empty. A star that flickers for reasons we still don't fully know. Worlds with no sun to call home. Gold forged in a collision older than the Earth. 72 seconds never explained. A single extra particle in a billion that became everything. A crystal that never runs down. A liquid that climbs its own walls. A twin, quietly younger, simply for having traveled. Galaxies bending light into rings. Trillions of ghosts passing through you every second. A shape we still can't fully confirm. A box that stays uncertain until it's opened. Lighthouses spinning in the dark for no one. And somewhere above you right now, two galaxies already, slowly falling toward each other. None of it needs solving tonight. It never did. If your eyes are already closed, that's exactly where they should be. And if they're still open, just a little, there's another quiet mystery waiting right after this one whenever you're ready. No rush, no sound, just drifting gently